Thrusters at the sides of a spacecraft help it stay oriented by thrusting a small amount of gas, moving the spacecraft in the opposite direction. The problem with this type of system is that it requires a propellant, something that takes up both weight and space on the spacecraft. An alternative? The use of reaction wheels. As opposed to the fuel used for the thrusters, the reaction wheels are driven by electric motors, which are in turn powered by the spacecraft's electrical power supply and are controlled by the spacecraft's onboard attitude controller. Reaction wheels moves the spacecraft in the required direction by the transfer of angular momentum and Newton's third law. For every action, there is an equal and opposite reaction. Spin the wheel in the clockwise direction and the spacecraft moves in the counterclockwise direction, and spin the wheel in the counterclockwise direction to move the spacecraft in the clockwise direction. Spacecrafts typically have 4 reaction wheels, 3 to control the roll, pitch, and yaw angles, while the 4th acts as a backup. This project involved the modeling, simulation, design, and implementation of a single-axis reaction wheel that is capable of swinging an aluminum tube, acting as a spacecraft body, from a downward stable position to an inverted position and thereafter stabilizing it. The purpose was to show that despite the system being an underactuated system, where the control inputs are less than the generalized coordinates, the system can easily be controlled using simple controllers. System equations were modeled using Lagrange and the system simulated in MATLAB and Simulink to observe whether it behaved as expected or not. 3 controllers were designed for stabilization and compared with one another so as to select the best one, whereas the simple bang-bang controller, in other words an on-off controller, was designed to pump energy to the system depending on the pendulum speed and angle so as to swing the system up close to the catching region, where the controller would then switch to the stabilizing. The controller was implemented on an Arduino Uno that communicated with the encoders and the motor. The stabilization test was conducted first to experimentally find the catching angle. Oscillations can be seen to be present, which are caused by the dead bend of the motor and the wires hanging around the side that cause the pendulum to always lean towards that side. Hence, the wheel would always try to oppose the motion more in one direction than in the other, as can be seen in the video. A better design that aligns the centers of gravity could help minimize these oscillations. The swinger plus stabilization test was then conducted as seen. It was shown that the control strategy worked for such a system, further proving that reaction wheels can be ideal in attitude control. Thanks for watching.